Also in the 1960s, Robert McNamara showed up at the Pentagon. Robert McNamara had been a statistical analyst in the Army and then a statistical manager at Ford Motor Company. And when he showed up at the Pentagon, he continued the process of statistically analyzing problems. And he really pushed the idea that strategy, policy, acquisitions should be made based on analytical studies of battle and the use of weapons and the interactions of different kinds of weapons. He really pushed that idea. Prior to that, most decisions were made based on the experiences of soldiers who had been to war and said, this is what I think is best for our Army, Navy, Air Force, whatever. He really pushed the idea of studying it scientifically. Then about 1976, everybody starts getting into the computer wargaming business. Why? Well, because for the first time, everybody can afford a computer. We start to emerge computers that are powerful enough and affordable enough that lots of organizations can buy them. And so around the 70s, all kinds of models start popping up. And if you had a family tree showing the birth of simulations, you would see that there was a baby boom in the 70s. And some of the models that were baby boomed in the 70s were the Ida Hex model, the McClintock Theater model, Janus, and Tack Brawler. Those last three are still being used today in different forms. After they built all of these models, they started looking at criticizing them, describing what they don't do well. And they came up with this list of things in the 70s that analytical models did very poorly. The first was it had a very poor integration of political and military context. In fact, there was almost zero political context in these simulations. There was a very poor treatment of high-level command decisions. Good treatment maybe of shooting somebody, but bad treatment of decision-making and allocating forces in different patterns. Overemphasis on quantifiable factors. Lots of models that described how attrition happened, how detection happened, how movement happened. Very few algorithms describing morale, training, the national will to fight, those kinds of things, not described in the model at all. Simplistic treatment of maneuver and operational tempo. The speed at which you attack the enemy had no effect. Attack him slow, attack him fast, no big difference. Little perspective for military strategy, force structuring, and arms control. And finally, exclusive focus on nuclear exchange. These criticisms are almost all valid today. The last one, not so valid. We've kind of lost our focus on nuclear exchange. But most of these criticisms are still true of the models we're building today. That's kind of alarming. Here we are 25, 30 years later still doing the same kind of modeling, or not doing the same kind of modeling. In response to those, Trevor Dupuy created a method he called the quantitative judgment method. The quantitative judgment method quantitatively defined how combat happened, but then it added military judgment. The experience of people who had been to war and their evaluations of factors like the national fighting quality, morale, surprise, leadership, training, all those different, the experience of the forces engaged, all those different effects which were very soft, kind of mushy, not very analytical. And at the time, people did not accept this approach at all. They said, this is not right. You can't just throw in a factor of 7 and say it causes the outcome to be what you experienced during your tenure in combat. So he was very discouraged by the fact that people didn't like the judgment part of his QJM module. However, jump forward a little bit, and the RAND Corporation is building the RAND Strategy Assessment Model. RAND Strategy Assessment System is a war game which relies very heavily on the use of expert systems. Expert systems in which they have encoded the behaviors of specific military positions, specific military leaders on the Soviet side. A model which very accurately captures how the Soviets are going to fight us in World War II, and how we're going to respond, and how that battle is going to turn out. Excellent model of that behavior. Very valuable model. One of the things the expert systems brought into respectability was the factor of judgment. You put in information that the expert told you. His judgments became an acceptable part of modeling. So the ideas of QJM now are seen as a natural part of modeling. Now this model had a great lifetime. Unfortunately, a bad thing happened for this model. The wall fell. The Soviet Union disintegrated. And all of a sudden, all of the expert systems that drove this system were no longer valid. You couldn't apply those expert systems to how Saddam Hussein is going to react in Iraq. And that was very difficult. So this simulation largely got shelved. But it was a great system at the time. And we learned a lot by building it. Tag Brawler, 19 Eras era simulation in which air-to-air combat is conducted with different planes of different types, with different missiles, does the maneuvers between them in response to missile launches. Built in 1987, still being modified and improved and name changed today. One of the things you should know is that a simulation often changes its name to get a new reputation. Often you'll find a simulation that you'll say, I don't know anything about that, and you'll find out it's a new simulation by the same name. It's a new simulation with a different name. Epstein's equations. Joshua Epstein was looking for a way to quantify combat in a very macro level, where you clump together not just one unit, but lots of units. And he invented this piston model. And the piston model essentially divides the battlefield into a flot, and then you take the piston and cut it in half. One half of the piston is blue, the other half of the piston is red. And as you pour your forces in there, they get aggregated or accumulated into the combat force of the red side of the piston. And they attrit the blue side, and that attrition causes the piston to slide backwards in the blue direction. And as that piston slides backwards, it gobbles up units behind it, in fact reinforcing itself. And then the piston slides back the other way. So these pistons are all sliding back and forth on the battle based on how much you're attriting the person on the other side. Now there's a rule here that says these pistons must always be contiguous. They can't slide apart. You can imagine like two pistons pushing each other apart and creating a gap. Well, the big problem with that is now the red forces can march through that gap and go nose to nose with the blue force. And you haven't written any algorithms that know how to adjudicate battle between two units facing each other. All of your combat algorithms are in the pistons. So the pistons have to keep the red units and the blue units separate, and therefore they remain contiguous. That idea is used in a model called the concept evaluation model. And the concept evaluation model was applied during Desert Storm to try and understand how attrition was going to come about during the war. We also fielded the extended air defense simulation and tried to understand the effects of our airstrikes against the enemy and the effects of their air defenses against our airstrikes going in. So CEM and EADSEM were both being operated during Desert Storm to try and quantify and mimic the effects that we were seeing in battle today and tomorrow and the next day, right then on the battlefield. And finally, the core battle simulation was being used back here in the United States to try and find out what our attrition levels were going to be. When we go against the third largest army in the world, how lethal is that going to be to our forces? What's going to happen in the future in systems analysis? The most interesting thing to me, you're going to be sitting down designing a car, let's say. We're taking this out of the military context. Designing an automobile for General Motors. And as you design this automobile, you're going to need parts from the transmission manufacturer, the water pump manufacturer, the guy that makes the mirrors, the guy that makes the headrest, the radio, your onboard computer, etc. And when you need a model of that piece, you're not going to build it yourself. You're going to go on the web. And on the web, you're going to go to the manufacturer of those parts, and he's going to have a model of his transmission, of his water pump, of his whatever. And you're going to download that model and load it into a tool, and you're going to construct your model of this new modeled car from those parts, those models you pulled off the internet. Now the first step is building parts that look like the part you're downloading, that fit like the part you're downloading. But the second part is to make them interface together so that you can take an engine from one website and a transmission from another website, tie them together, and actually have the transmission and the engine work together. That's what people are working on right now. They want to be able to define models in such a way that there's a standard way for them to interact together. VRML allows you to define 3D objects so that you can see if it fits right. But there's nothing right now that describes if it functions right with another model, whatever it's going to be called. That's one of the most interesting things that's going to happen in the future, given that we get enough money to do that. Here's the best reference on this topic. It's not the most current, it's the most interesting. Methods of Operations Research by Morse and Kimball was written in 1950. It was republished recently by the Military Operations Research Society, which is where you can buy it. It's a fascinating book. I have a bachelor's degree in applied math, which means operations research. I never read a book that was interesting like this. I read lots of books on OR, and they were all awful. I would recommend, if you want to know about operations research, read this first, and maybe you can find something a little bit drier to become more current with.